And continuing our panel's focus on infrastructure and measurements is Alex Kwasinski, University of Texas at Austin. Go ahead, Alexis, sorry, excuse me.
Okay, good morning. So I will talk a little bit more about now power and how they affect communication networks. And my focus, I'm going to talk, going to do a quick overview of different communication networks and how they are affected by power and other infrastructure issues. Since I'm going to go a little bit fast to cover all the material, there are some links where you can get more details and information about what I'm going to discuss. And the information that I get, the observation I'm going to do is actually from field observations. I do damage assessments. I've been doing that since Hurricane Katrina. The reason why I tend to follow, and that's the one that I did for Sandy, the reason why I do damage assessments is that you would find incredible how people, two persons in the same situation, under pressure, they may say different things. It's unbelievable when you hear people talking about what happened, different stories for the same situation. So when you see what's going on in reality on the field, that's something, an evidence that you would not get from people talking and describing what happened. So my focus is on power supply, and one of the reasons why is power supply, the focus of my discussion is because of Hurricane Katrina. And the point of this slide is showing that even though Katrina produced a lot of damage, most of the outages that we had, communication outages that we had during Katrina were originated in power issues. And that's something you can see in many disasters. In Japan, for example, you would see that on the graph of the left is showing power outages compared with communications outages. And you typically see this in all disasters. You see power outages occurring first, and then communications outages following with a delay because of the energy storage that you typically have in most communication sites. So let me talk a little bit about Sandy and start talking about the wireline telephony networks. And what you see, this is the main central office that you have in Lower Manhattan, 140 West Street from Verizon. And the main issue that they had, there were not so many power issues in affecting central offices. But what you had was the key facilities that were flooded during the storm surge of Sandy. And you see there water being pumped out of this facility. And of course, you see a genset there. That portable genset is indicating that there were damage on the power facilities on this location because of the flooding. So the question is, well, how you can prevent that? And some of the solutions are placing the infrastructure on higher floors. And you see on the top right, that's the Lavaliette. That's just north of Seaside Heights in New Jersey. And you may ask, well, why you didn't hear about an outage or a problem in that central office if there was so much damage in the New Jersey coast? Well, because they had a genset on the first floor. They didn't get that high. The storm surge didn't reach that facility, and it was spared from damage. So the concern usually when you place power equipment on higher floors is mostly a structural problem. For example, let's take batteries. Batteries are the most dense components that you have in your central offices. They weigh a lot, and that creates a structural problem. If you put it higher on higher floors, that makes the entire building more susceptible to damage. But if you design the building well, that may not be much of an issue. And that, to prove that, I'm showing this is the Onagawa central office in Japan, right after the tsunami. The central office is the building with the house on top, so it was completely submerged under the tsunami. Yet, if you look at the interior of the power room, you see the batteries behind that. There was no structural damage on this building. That's because you can design buildings to place the power infrastructure on higher buildings and still make the building survive the tsunami. And this is high forces. This is one of many buildings. In many cities, you see that the only remaining building, or one of the few remaining buildings, from the tsunami was the central office, and that tells something. You see that the solution implemented in many places here was to use Sandbox. That's actually not a very effective solution. If you look in Japan for inspiration, you see that they use actually watertight doors. And they are pretty much like submarines, and that's one of the reasons why they survived the tsunami so well. So you see pretty much walls surrounding with floodgates. You have watertight doors, and that's the Kamaishi. You may have seen video of the waves striking the city, and that central office went at least 2 floors underwater. What didn't sustain much damage because water didn't get in because of the watertight doors. Another problem that happens, and that happened with Katrina, happened in central office that floods, and this is again going into the 140 West Street facility, is that when you get water in the lower floors, you may have damage into your copper facility. That's because you may lose pressurization on those cables. Those cables have pressurization. You lose, even when you have gels in the cables, you may not prevent water damaging, for example, at the splice level, those cables. And what eventually happens, you have a higher failure rate on those cables, and the solution that was implemented after Katrina and in other disasters, even to replace some central offices, was to use fiber optic systems. You replace copper by fiber optic. And the good advantage that you have in these systems is their flexibility. When you need to replace, after disaster infrastructure, one question that you have is, what's your demand? In many areas in New Orleans, there is still the demand is much lower than you had before Katrina. So how many copper cables pairs you may want to have there? You don't know. I mean, it's very difficult to know. If you are fiber optic, then you don't need to lay out a given number of pairs. You know that you can deal with that traffic. So you may increase resiliency of your network by adding these components. But the main disadvantage are power issues. You have many sites now requiring local power supply, so you may deal with more resilient network, but less resistant networks. And that's something you may need to consider in these events. Let me go into wireless networks, and one of the main problems in wireless networks, again, power, and now power is affecting distributed network elements, cell sites, base stations. One problem in particular with Sandy was the number of base stations located on rooftops. In some rooftops, you have standard sockets where you can connect a generator that you can take on the street. The problem is that there are many buildings where they don't have these standard sockets, and then you have the problem on how to connect a generator to the roof, and you need to get access to your roof, and that ends up being a problem and delaying restoration. So that was a problem with Sandy. What are the options that you have to power cell sites? The most common options is using diesel generators, portable generators, or fixed generators. One key thing that you see in many places, specifically here in the United States, is after disasters, you see multiple deployments of generators in a cell site. You have a cell site that is shared among a number of network operators, and each one deploy their own generator. That's okay. The problem is that increases your logistics needs many times. Everybody needs to refuel those generators, and everybody needs to deploy those generators. If you can coordinate that, then that would be reduced. Other solutions are propane tanks, propane generators. What you need to be careful there is to put them in a way that they are not damaged, as the one on the bottom left, or using fuel cells. There are a number of base stations in the Gulf Coast using fuel cells too. Let me go into another network now, cable TV. The problem with PowerNet cable TV is on the outside plant, and even though in some part of the Gulf Coast you see natural gas generators, you also see that those natural gas generators that are pad mounted, they can be damaged from the storm surge. That's an example of Katrina in the middle. After Katrina, and then after Isaac here, after Katrina, the generator on the ground was damaged. So after Isaac, they needed to put what they do everywhere, which is to put the generator on top of the equipment on the pole. That's very unsafe condition. You see that everywhere. And then into the network evolution, you see more distributed networks, and that means people also need to power their own devices. So now let me talk in the remaining minute about the power grids. Then go into the source of the problem. The source of the problem is power grids. And if you observe power outages during disaster, you will see that damage is limited to, intense damage to a very small area. Most of the area affected by disaster, by a hurricane, exhibit very little damage. Less than 1% of the components may be damaged after a hurricane like Ike in here. Yet power outages are far more extensive and last longer. That is indicating a very fragile system. And the reason why power grids are so fragile is because they have a centralized control and generation architecture, pretty much. So you would see, for example, here after Isaac, Grand Isle, which was close to where the hurricane made landfall, you see one pole damage among many of them, maybe 100, and you see half of the island without power. That's why you lose so much power after a hurricane. This is a very fragile system, the power grid. So what the network operators need to do is need to address those issues. You have two ways of solving the problems with power grids: working on the utility side or working on the network operator side. If you work on the utility side, the problem is still the same. You will, even with smart grid technologies, you have a very fragile network that's, you have a centralized generation and control, and you still need to send someone to fix that pole that I showed in the previous slide. At the network operator solution, you have the conventional solution, which is standby systems, which I'm showing here. And the only reason why communication networks implement this is because they need to overcome the grid availability, which is 99.9% of the time, into reaching 99.999% of the time, which is the requirement. And to do that, you have generator sets and you have batteries. Batteries are essential. You cannot reach that level required without batteries. And that means that air conditioning systems that are not receiving battery power, they have a lower availability than what they need to require. So the weak point is cooling in many places for communication networks. The solution is, one alternative solution is to add local power sources in what's called microgrids, and now these local power sources are your main source of power, not your alternative source of power like in standby systems. And the reason why you can implement that is, like I said, you have a very homogeneous distribution of damage, and damage only occurs in very small places. Most of the area exhibits little damage, and you can implement these local solutions then. The problem with having local power sources is that some of them require other infrastructures, natural gas, roads, and they might be affected too. Anytime you have any dependency on something, if you want to overcome that dependency, you may use local storage. If you have a dependency on data, you wouldn't put that data on the cloud. You would store that data locally on site. So if you have dependency of power, you will store energy locally. So that's one solution. The other solution is diversifying power sources or use renewable energy sources like photovoltaics. The problem with photovoltaics is that they are they have a large footprint, and they also are variable output. The way you solve those problems is through local energy storage and source diversification. And let me conclude that. I mean, this is an example of how you could use local solutions in communication networks. And these are my conclusions of what I've been talking so far. Thank you very much. And I'm pleased to hear your questions later on.
Thank you very, very much.